All right, guys, the first fundamental theorem of calculus, what's so special about that is that the first fundamental theorem of calculus tells you that if you know the antiderivative of a function, you can evaluate the definite integral by first finding the antiderivative of the function and then evaluating the lower and upper limits of that function. And that'll give you the area up under the curve, or aka the definite integral. The second fundamental theorem of calculus is special because it says that the inverse operation of integration is differentiation, and vice versa. The inverse operation of derivatives is integration. In other words, whenever you take the derivative of an integral, they cancel each other out, and all that you're left with is the original function. Okay? So let me say that again. Whenever you take the derivative of an integral, or whenever you take the integral of a derivative, you're only left with the original function. The reason is because they cancel each other out. Like, for example, let's say you want to take the derivative of the integral from 2 to x of 1 plus t cubed dt. Well, the first thing I notice is that this is a constant, and this is just plain old x, and it wants you to take the derivative of the integral. Well, your answer is just simply f of x, which would be the square root of 1 plus x cubed. And so that would be the answer to that problem. Now, you're probably wondering, well, what happens if you don't have just plain old x? What if you have something else there? Well, that's when we're talking about a composite function. So let's say that you don't just have plain old x. Let's say you have some weird looking function there. The only thing you do differently, your answer is still going to be f of that value. You just make sure that you go back and you take the derivative of whatever that upper limit is. So, for example, let's say you wanted to evaluate the derivative of the integral of sine of t dt from negative 2 to x squared. Notice that this is a constant, but notice that the top one is not just plain old x, it's x squared. Now, my answer is still going to be sine of x squared, because I'm just going to plug in that x squared there, but I have to take the derivative of x squared, and so that's going to give me 2x, so my final answer is going to be 2x sine of x squared, and that would be the answer. All right, another one to look at would be if we wanted to find the derivative of the integral from 1 to 1 over x of cosine cubed t. Notice that this is a constant, and also notice that this is not just plain old x. So you can rewrite cosine cubed of t to be, I'm just going to say rewrite it, cosine of t cubed. All right, so what I'm going to do is first I'm just going to plug in 1 over x into my t, so I'm going to have cosine of 1 over x cubed, but then make sure that you go back and you take the derivative of 1 over x. The derivative of 1 over x would be negative 1x to the negative 2, and then this is cosine of 1 over x cubed. Now, you could leave it like that. However, I'm just going to clean this up a little bit and say my answer is going to be negative cosine of 1 over x cubed over x squared. And that would be the answer.